For our 15th year in the Hamptons and almost 3 decades throughout the country, we are now bringing the Hampton dialogues to you digitally. And we wish we could be with you in person, but today we're bringing you this program digitally, and we'll have ample time for question and answers. And as we always have over the years, we have brought leading experts in particular topic areas. And today, our topic is focused on Cancer 2020, our new cures in sight. And in February of this year, as many of you might be aware, when Jonathan and I returned from our medical conference in Johannesburg, I spoke to him and told him that I needed not only his leadership at the PCF and Howard Souls and others, but I needed them to take the leadership to look at everything that has occurred in cancer research in the last 30 to 40 years and see what would be usable to address the coronavirus, the COVID-19 pandemic. And today we're going to touch on one of those areas, but our program on Saturday morning at 10 o'clock on the East Coast and 7 o'clock on the West Coast will focus on COVID-19 particularly. So let's talk a little bit about what's occurred in the last 6 or 7 months. And one of the things that we focused on was creating these podcast series. And we put out the first book, which you can get if you'd like. And we have now completed 103 podcasts, and the second podcast book will be coming out in the next 2 to 3 weeks. Related to cancer, we interviewed maybe out of the first 100, maybe a third had worked in some area on cancer in their lifetime. And we started with Francis Collins, the head of the NIH, but Ari Beltran, Jim Allison, Pam Sharma, Peggy Hamburg, Eric Lakowski, and others. And you can read all of these if you'd like. But the side effect of focusing on this issue was the potential collateral damage. And you don't have to go any farther than realizing that the number of reported diagnoses of cancer just in the United States this year, depending which cancer you're focused on, is down 20 to 40%. So therefore, we recognize that cancer has not gone to sleep, but we recognize that thousands or millions of people who've had potential life-threatening diseases elected not to go into medical centers and be diagnosed, and so we will be seeing these issues. There's also other issues that have come up, and they are what's happened with medical research, and Jim Allison and Pam Sharma and Steve Rosenberg at the NCI all talked about the shutting down of physical research laboratories during this period of time. But at the same time, throughout the world, research has gone on and has changed, once again, will change the face of cancer treatment and cancer outcomes for the better. I'd like to give you just a few statistics here before I turn it over to Jonathan. Probably the one that we all need to focus on is that the first sequencing of the human genome, an entire sequencing of your body, took more than 10 years, led by the first podcast interview, Francis Collins, and cost billions of dollars. To put that into sequence, that was 2003 in completion. Now, the cost of sequencing a human genome, your genome, for routine cancer care cost about $200 wholesale, 1/5 of an MRI, and less than certain chest x-rays. So the cost of sequencing and determining what your issues are is now available for almost every single person to do. And so this has dramatically changed research as we know it. Computers 1,000,000 times faster. Data storage costs down 1/1000th have allowed us to do things and imagine things we could have never achieved before. And just a simple example is that 11 days after the DNA of the virus was released, Moderna, and there's an interview in the podcast with Tal Zaks, the chief medical officer of Moderna, and he will be on the program tomorrow morning, along with other leaders such as the CEO of Regeneron and others, on the COVID-19. But 11 days is all it took for them to begin their vaccine program. And within 3 months, their vaccine was in human beings due to technology that's available to you today. The other thing I would point out to you is that, as we have discussed over the years, once we sequence and once we understand the mutations, we discover that cancer, a particular mutation, is not related to any one area in your body. And more than 70 cancers have mutations similar to prostate cancer. And Jonathan will talk about it. And so the solutions that we are finding in prostate cancer have already shown to have applications in other forms of cancer. But one of the things I want to stress on this panel is that many of the potential solutions and success that we are going to have in treating COVID-19 lie in work that we have done over the years at the Prostate Cancer Foundation to try to reduce the death rate and ultimately eliminate cancer as a cause of death. And today, with Deborah Scher with us today, Jonathan will set the stage for a discovery and analysis that was done at the Prostate Cancer Foundation in 1999 on the fact that using ADT drugs, androgen deprivation therapy, results quite possibly in the prevention of the virus from going to your lungs, since it needs access to testosterone for TMPRSS2 in order to apparently open the door to your lungs. Podcast 50 in the book with Dr. Simons and 5 others discusses this issue, and a clinical trial was begun a couple months ago on this issue to try to identify these drugs, which are often generic and ones that are fast acting but only last for 30 to 40 days, can quite possibly prevent the movement to your lungs of this virus and serious side effects. The idea of controlling the cytokine storm, the side effect of all the work that we have led in immunology since 1994, quite possibly by stopping this, which occurred in cancer treatments, we can prevent this virus from going to your lungs and prevent most of the deaths that have occurred in the past and might occur as a side effect of this virus in the future. So in many ways, there are more than 70 antiviral, anti-cytokine, vaccine, and other products out of the more than 500 that are on the tracker at Faster Cures, the sister organization of the Prostate Cancer Foundation, that have their background, their traces, and their discovery to work which we had done in cancer. And with that, Jonathan, I'd like to turn it over to you. First, to kind of give a summary of this dual responsibility you've had over the last 6 months, and to introduce our panelists today. So thank you for joining us today.
Thanks, Mike, and good morning to everybody that's joined us. I'll introduce our speakers in a second. Mike, we sometimes forget, is responsible for creating the foundation, that's now reduced the death rate from prostate cancer by 52% since his diagnosis in 1993. And now there are over 3 million prostate cancer survivors around the world. And if you can take on a life-threatening illness and make that enormous contribution relentlessly, it seems obvious you would apply it to the greatest public health crisis certainly our country may have faced in 100 years. The second point is, like Mike said so elegantly, is that the road to curing COVID, preventing COVID, understanding COVID and SARS-CoV-2 runs right through lots and lots of cancer research. Deborah Scher will talk a little bit about the VA is probably the least publicized and most important platform right now for ending COVID-19 deaths in terms of clinical trials, built on a platform of how Dr. Beltran, Dr. Feng, and I take care of cancer patients. Literally, the new precision care models for oncology are being applied in real time to treating COVID. And just like you'll hear today about the revolution that the human genome's brought and the momentum that's brought to cancer care, and understanding how genes work and then how the software called epigenomics works from Dr. Feng, we hope to leave you with just scientific based optimism if we can continue to stay as focused as Mike on putting the right people in the right places with the capital to end COVID-19 and get back to finishing the job in prostate cancer, where we have 48% of the death rate still to finish off, and applying a lot of that to accelerating the end of cancer as basically as a burden on humanity. My speakers today are all PCF in a way, PCF funded, all investigators, all world leaders, but they're all part of the continuum that if you understood how a gene worked, you could reduce and ultimately cure every form of human cancer. So what I thought I'd do is, Sean, could you put the slides up for a second, please? I want to thank my colleague, Sean Grimes. Mike needs no introduction. I'm the president and CEO of the Prostate Cancer Foundation, and as Mike said, I'm also leading the R&D task force part of Faster Cures on COVID-19. And my colleague, Howard Sewell, in the panel with Mike tomorrow will tell you really in real time about what we've come to understand about SARS-CoV-2 up to yesterday. But our speakers are Himisha Beltran from the Dana-Farber and Harvard Medical School, who was a PCF young investigator, Richard Lefrak young investigator, has gone on to become a world leader in precision oncology. She'll set the stage. Deborah Scher will actually hit cleanup today because all this comes together in how we're using as a new national model the Veterans Administration for all of American healthcare. Felix Feng will hit second because we've got baseball back, although the home run challenge, the silver anniversary of that's deferred till next year. Felix Feng, who's the vice chair of radiation oncology at the University of California, San Francisco, world leader, will tell you two things that we want you to take away. One is radiation may be used to cure metastatic disease, not just primary disease. And Dr. Feng and his colleagues, as a physician scientist, understanding genes, has gotten deep into the software of what makes them actually active or quiet, or turns them up or turns them down. This word epigenomics, if there are four things, because this is a Milken operation, if there are four things, not three things you should take away. If it was plastics to Dustin Hoffman in The Graduate, it's epigenomics this year, including their role in the microbiome, or the our bacterial friends and enemies. And Chris Haiman has taken basically the human genome and human genetics and done work in the other thing we want you to take away from today, which is called polygenics, or polygenic risk, or the possibility that every family practitioner, every pediatrician could have understanding all 22,000 genes and the software running them could be proactive in your healthcare about catching cancers perhaps a decade earlier by understanding basically how all the genes are working at once based on the genes you got from your mother and father. So Chris will come after Felix. So with that, Sean, you want to bring up the Misha slides? Great. So Misha, we'd like you to take this, all our friends, imagining they're on a nice Hamptons porch or some nice porch in a late August sunny morning. Could you answer a couple of these questions? What's precision medicine for prostate cancer? Why is it the paradigm for taking care of, like Mike said, over 73 other forms of human cancer? Why is it transformational? And what by 2025 will cancer care even look like with all of this?
Sure. Thank you, Jonathan. Good morning, everyone. It's really wonderful to be here. This is really a topic that is near and dear to my heart, because even in the last 10 years, doing research in this area and taking care of patients, this has really transformed the way we think about cancer and the way we care for individuals. And I thought it would be good to just kind of step back and think about the term precision medicine, because this is something we hear about a lot when we think about research, cancer, healthcare delivery. But it's really an approach that is really quite simple. It's, can we more precisely deliver healthcare or medicines to patients by matching the best therapy with the right patient? And by doing this, we can deliver better outcomes. And this is extending beyond our traditional factors. You know, traditionally we think about things like the physical exam or laboratory values or radiology, pathology. Now we're taking it kind of one step further, recognizing that every individual is different. And by studying the molecular features of people and their cancers, we can make more precise or personalized decisions when treating people diagnosed with cancer. Next slide. So in cancer, a lot of precision medicine has focused on genetics or alterations in the DNA, because we've known for many years that cancer is a genetic disease. And as Bert Vogelstein, one of our pioneers in cancer genomics, said many years in the 90s now, that these DNA mutations or alterations can drive cellular multiplication, increases in tumor size, disorganization, and malignancy, the hallmarks of cancer. But despite knowing this for so many years, it really wasn't until recently that we had the capability to actually do this in real time for our patients that we're treating in the clinic. Next slide. And the reason for this is it's really complicated. There are billions of letters in the DNA, 24,000 genes, a lot of repetitive sequence, and each person, we're generating massive amounts of data, and then we expand this through hundreds or thousands of people, and we really require big data scientists, computational tools to be able to have clinicians like me interpret this. And we can now, on the left, you can start to map out patterns of DNA alterations within a cancer cell by sequencing the genome. And then we can actually start to interpret this and figure out what is in the cancer, but also can we learn where did that cancer come from, where is it going, similar to a subway map, thinking about all the intersecting patterns or pathways that occur within a cancer cell. And this is allowing us to develop ways to intervene and treat cancer. And thanks to the Prostate Cancer Foundation and metastatic prostate cancer, there's been over thousands of genomes already sequenced, and this has really led to changes in the way we practice and the way we treat individuals with prostate cancer with targeted drugs. Next slide. So this is just a schematic really showing how the paradigm has shifted. We are now in the clinic at places like Dana-Farber, UCSF, all over now, not just in academic centers, but in community practices as well, performing genomic sequencing and developing studies to really understand how to best use them to inform not just targeted therapies. PARP inhibitors are one class of targeted therapies that were recently approved for prostate cancer patients, but there are a number of others in development that are where response is influenced based on the genomic or the molecular features of a patient and their cancer. Next slide. So recently, the FDA approved a class of medication called PARP inhibitors, 2 drugs, olaparib and rucaparib, for a select subgroup of patients with prostate cancer based on the mutations found in the cancer's DNA. And this is really has made precision oncology a reality for every prostate cancer patient because, and this is really, I think, a paradigm of what I said. You match the best therapy with the right patient, and not everybody will respond. And now we are now doing this in real time, and there are many more drugs, I think, that are in the pipeline in a similar fashion.
But a key that I do color commentary, given the everyone knows. But a key thing is you have to have your biopsy sequence, right, Misha? Like Mike said, the precision comes in having the DNA read to match the right drug or the right treatment.
Yeah. And I think one of the challenges, getting to the next slide, is that as we're sequencing more genomes in cancer, and especially in prostate cancer, we focus a lot on the common alterations. And so this is a plot where you see the frequency of alterations plotted against different genes. And a lot of what we focus on are the ones that are frequently mutated in many patients with that particular cancer, because we think, well, those are the ones that are driving the cancer, and can we develop drugs for that subset? But in prostate cancer, there is this long tail, and what that tail represents are mutations that are present not in everyone, but only a very small fraction of individuals. Less than 5% of people with prostate cancer, their tumors will harbor one of these mutations. And these have been particularly challenging to study because they're not frequent. But we do think that they're important in conferring response to therapy, and may be predictive of response to help us develop novel therapies to target even rarer subsets based on the genetic alterations in that cancer. And we also know, next slide, that there are patients that achieve exceptional responses to therapy. And likely some of those tail alterations, or potentially even alterations that are outside the genome, are helping to confer response. And so we still have work to do. This is a patient of mine, a 61-year-old with advanced prostate cancer, who had developed progression after many lines of therapy, including androgen deprivation therapy, chemotherapy, abiraterone, anti-PSMA therapy on a trial. And he went on a clinical trial of ipilimumab, which you may know is an immunotherapy. And that trial actually went into phase 3 for prostate cancer. And the trial was not positive, meaning not everyone responded well to ipilimumab. So this drug did not get approved for prostate cancer. But this patient, my patient, had an extraordinary response. His PSA went from 72 to 1.4. You can see plotted. His PSA dropped almost immediately on treatment. His scans, his images, his cancer nearly went away. He had a dramatic improvement in symptoms, and he ended up coming off of the drug because of side effects, and he did not progress and did not require any additional treatment for almost 2 years. And so this I would categorize as an exceptional responder to a drug that does not work in everyone. We sequenced his genome, and we did not see anything that we would have expected to confer a response to this drug, things like mismatch repair or microsatellite instability, things that have been associated with response to immunotherapy and other cancer types. But he did have a lot of these rare alterations, and I think it's really been our obligation as a field to really understand exceptional responders, because you can imagine that he's not the only person that would achieve a response like this to ipilimumab. Next slide. So we're thinking ahead and thinking not just about studying this long tail and understanding exceptional responders, but what do we actually do with this? And this is a very early concept, but we've been, as a field, thinking about novel ways to bring treatments to patients based on not just their DNA alterations, but integrating things like RNA and other biomarkers, and thinking about treating patients without requiring the numbers needed for a large trial, but being able to cast a broad net to identify these long tail alterations and allocate them to specific drugs in a sort of basket trial sense for prostate cancer specifically.
So this one is interesting because we have a lot of people that may be 3 decades away from the algebra they had in high school, but get the fact that if you're a patient and you have a mutation that we could put you in remission for, but only 2% of prostate cancer patients have that mutation, but 7% of ovarian cancer patients have that, and 9% of breast cancer patients have that, and 14% of colon cancer patients have that. All those patients that have the targetable mutation ought to be in a basket and get the drug, not based on, like Mike likes to talk about, not based on the anatomic, but on the genomic. And that's going to require multi-center collaboration. Deborah Scher will talk about this in the VA as a model. But it's also going to require patients that are aware that they need to know what their mutations are and where they are basically lined up against the long tail. But we're very excited about this because these other channels of looking at these tumors also will be reduced to practice in the next 5 years. You see drug A, drug B, drug C. We need to make more drugs very specifically against these new targets, which we know are central to making the cancer tick. Thanks. Keep going, Misha. It's great.
So if I could look into the future and think about where we're going to be in 5 years, I do think that sequencing for every patient, not just with prostate cancer, but all cancers, will be a reality. We want to know about the common alterations. We also want to know about the uncommon ones, those long tail alterations. And as Jonathan said, to learn from, to be able to provide insights to other cancer types as well, as cancers may be driven. These infrequent mutations are also existing in other tissue of origin cancers. We will be using these genomic reports to make better decisions. And this is not going to replace what we do today. When we see a patient, we do imaging and get pathology, but this will just help us take it, again, to a much more precise or informed level. And now I think that this is much more accessible, not just to people in distinct centers, but there will be broader accessibility to genomic expertise, drugs, and trials. And I think a lot of this will be due to the fact that telemedicine is really a reality now. And this is something that I predict will stay. It happened overnight with COVID-19 and with the pandemic, and I think will help as far as cancer care, really bring people together and be able to help us match drugs with patients in a more effective way. And the next generation of precision assays are coming. We are moving beyond DNA, and there are as technologies are moving fast, and it's not just the genome now that we are going to be integrating into the clinical decisions in real time for patients beyond research. Next slide. I like this figure that was published in a journal not that long ago, where you can just really see how a lot of what I mentioned was focused on the genome, but you can see all these other layers of big data that are happening within the cancer, the proteome, the transcriptome, the epigenome, which I think we'll hear about. And each one of those requires just as much analysis as the genome. And now we want to integrate all of that. And this is really an opportunity for artificial intelligence, and something that I do predict as we move forward, we will have a blueprint of not just the genome, but all of these factors, and whether it be in 5 years or further from there. But I do think that's a field that's rapidly moving quickly. Next slide. I think that might be all I have.
Misha, we'll save you have several questions in chat, but Sean, can you just go back to Misha's last slide for a second? But the Hamptons, so the future for a cancer patient, the future is now, but big data, if you want precision care, you want all these elements of data for you. And big data science is this huge and important area where we think cancer research in cancer care are going to lead. Mike talked about in 10 days, this was one of these levels was simply applied to COVID-19 and launched over 100 vaccine efforts. And that's just the one at the genome. The second one at the transcriptome also giving us ideas about anti-COVID drugs. But the oncologist you want to take care of you is very familiar with how big data for caring for a cancer patient works. So thanks, Misha. Can you put up Felix Feng slides? So Felix is a very special clinician scientist and physician scientist like Misha. He leads the UCSF prostate cancer research program in the laboratories there, but he's a practicing radiation oncologist. And I wonder, Felix, if you could, just taking us through these slides, start with what's happened, let's say, in the last 18 months on how radiation therapy, which is used to treat 47 out of 100 cancer patients, receive radiation therapy in the treatment of their disease. And of course, radiation can be curative in primary tumors or early cancer, but there's a revolution going on in using radiation therapy to treat metastatic disease. So I wonder if you could tell us a little bit about that, and then help our friends in the Hamptons learn something about epigenomics and why by 2025 this is going to be a central part as well in taking care of cancer patients.
Absolutely. So thanks, Jonathan, for inviting me to present. Misha and I graduated from the same Prostate Cancer Foundation Young Investigator class a decade ago. And so for the last 10 years, I've had the pleasure of speaking behind Misha. My slide is actually on what you've asked me to talk about as the second part of my section. So the first part you've asked me to talk about is a revolution in radiation oncology or across cancers. And Jonathan, I think the word revolution is quite apt in the sense that if you look at the last 2 or 3 decades of radiation for cancer, we've always thought that radiation should be used only when cancer patients have what we call localized disease. And localized disease means disease that's confined to either the area of origin. So in prostate cancer, it means prostate cancer confined to the prostate, or maybe to the lymph nodes around there, but not prostate cancer that's gone to the bones or someplace far away from the prostate. Thanks to 2 very pivotal trials in the space of prostate cancer, what we now know is that patients who have a limited amount of metastatic disease, a subset of these can be cured with radiation therapy. And that's actually paradigm changing, not only in the field of prostate cancer, but across all of cancer, in the sense that now we can use a treatment modality, radiation, that is widely available. We can extend it into a disease space, metastatic disease, where it really hasn't been used. And we can't cure all patients with limited metastatic disease, but a subset of them, 5-7 years after treatment, are free of disease. And the question is, who are those patients? How do we identify them early, and potentially how do we improve upon the current cure rates with radiation for metastatic disease? And the other point I want to bring up is that radiation has for a very long time been considered what we call a local treatment. It means that where you aim the radiation is where the radiation works. Where you don't aim the radiation doesn't work. But we might be changing that paradigm as well. And when I say we, I mean the field. And what I mean by that is that there's something called the abscopal effect. And that's a fancy word, but that's the word that basically means if you treat one spot of cancer with radiation, another spot that you didn't treat may actually respond. And that actually, we are starting to see a little bit more now because of the rise of immunotherapy across all cancers. And Misha presented some nice data on a patient who responded to immunotherapy. But it's actually mind-boggling to me in the sense that when I started the field of radiation oncology many years ago, I was trained with certain principles, and some of those certain principles was radiation only works where you aim it. And now what we see is that, at least for a very small proportion of patients, radiation, when given with immunotherapy, might work where you don't aim it. And so I think that, Jonathan, these are very, very interesting times of kind of great advancement in the context of radiation oncology for cancer. And I would say that thanks to the Prostate Cancer Foundation, research advances in prostate cancer are kind of leading the way. And so the trials that are being done in prostate cancer are important, not only for prostate cancer patients, but are beginning to have importance, for patients with other cancers, just as, we become leaders kind of in changing the paradigm, of how we can give treatment and so forth. Jonathan, do you want me to touch upon anything else regarding radiation before I switch?
The doctors who know all of a sudden that oligometastatic disease, which is, let's say, 3-4 sites of metastases outside, in our case, the prostate, not 20, but disease that we never talked about having curative intent with until fairly recently. Just explain that. The doctors sometimes say it's like spot welding, but it's not. What is the new form of radiation that's used that's very different and very scientific with curative intent for oligometastatic disease? What is that, Felix? And why do the cancer cells die?
Sure. And so for many decades, when we gave radiation for any cancer, we would give a little bit of radiation every day over the period of many, many weeks. Okay, and that was what I term conventional radiation. But over the last, few years, there's been the advent of newer forms of radiation that Jonathan is referring to, and these newer forms, there's actually multiple names for them. It's like different brands, but it's really the same principle. And some of those brands include the word stereotactic body radiation therapy, or SBRT. Sometimes called stereotactic ablative radiotherapy, called SABR. There's brand names like CyberKnife and Gamma Knife, but they're all the same thing. And they basically all revolve around the principle of giving very high dose radiation to a very small area. And due to advances in how we give radiation, and also advances in how we can keep patients in the exact same spot, every day for a couple of days, we're able to give, 5 to 7 times the amount of radiation to a spot that we were, able to do a decade or 10 to 15 years ago. And the reason why that's important is that at that point in time, when you start using those types of radiation doses, radiation indeed becomes the ablative. And the word ablative means when you aim something at a spot, you kill all the cancer in that spot. And so, back 10, 15 years ago, when we used to give a little bit of radiation every day for, 8 weeks or so forth, none of those radiation doses were ablative individually. And what we hoped was that over the 8 weeks together, there would be enough damage from the radiation to the cancer to kill everything. But now, within just 5 treatments, we can give the same radiation dose we previously gave over 8 weeks. And that is what we call SBRT, and that has allowed us to treat metastatic disease. And more importantly, in the era of COVID, switching, you can imagine, from a treatment that requires a patient to come to the hospital every day for 8 weeks versus one that can be done in 5 treatments. Not only is this, improving kind of convenience and quality of life for patients by, reducing the number of treatments, but it's also reducing the risk that they catch COVID-19 from being in the hospital. And so all of these advances, I think, are benefiting patients in a multitude of different ways.
Thanks, Felix. Teach us about epigenomics.
Absolutely. And so, as Jonathan mentioned, I wear 2 hats. I'm a physician on one side, like Misha, and also I'm a laboratory scientist on the other side, like Misha. And so, what I'm going to do is briefly talk about the word epigenome. And so, in order to talk about the genome, I have to first talk about the genome. And so, the genome is, as Misha mentioned, focused on DNA, and much of the field of genomics focuses on changes in the sequence of DNA or mutations, or changes in downstream levels of RNA. DNA is made into RNA. Can you move to the next slide? And so, but what I want to point out though is that nowadays, as Misha pointed out, there are multiple layers of data we can examine in a cancer cell. And one of these different layers is the epigenome. And so, you know, the epigenome is defined as chemical compounds and proteins that combine to DNA to turn genes on and off. And ultimately, this may control cellular biology as much as the genome, the DNA sequence itself. And so here on the top right, you can see DNA, being converted into RNA. But what you see on the left side of the screen is that DNA and the architecture of DNA is quite complex. And so we think about DNA as a strand of what we call nucleotide bases and so forth. But it turns out that the structure of DNA is complex in the sense that there are chemical modifications to DNA called, methylation that can make DNA more or less accessible and therefore turn genes on and off. There are also proteins called histones here that wind DNA up tightly into balls and therefore make it less accessible versus, if the open DNA where it's more accessible. And so on a broad level, what we realize is that cellular biology is complex. And right now, Himisha has shown that I think when you look at clinical trials for prostate cancer, precision medicine, much of that precision medicine is focused on changes in the sequence of the DNA. But I think if you look over the next 5 to 10 years and you look at opportunities for precision medicine, those opportunities are going to arise as we understand additional layers of biology, including the epigenome in prostate cancer and in other cancers, as we understand architecture of DNA and chromosomes and accessibility of genes that leads to certain genes being on versus off. Can you move on to the next slide? And so recently we did a large study where we profiled a component of the epigenome called methylation across 100 patients with metastatic prostate cancer, looking at the metastases themselves. And you can see what we call a heat map here, this area of red and blue. And in this area, every row, you may not be able to see the rows, but there's 100 rows on the y-axis. Each of these rows represents a different area of methylation in the genome, and every column, I'm not sure you can see my arrow here, every column represents a different patient. And so there's 100 patients here. There's a bunch of different areas of methylation. And red basically means higher areas of methylation, blue means lower areas of methylation. And when you look at these quote unquote heat maps, what you look for is differences in color. So you want to see certain columns that look different from other columns. And what you can see here is in the blue box, there's an area that just actually looks a little bit different from all the other areas. And that's actually what we identified as a subtype of prostate cancer that's hypermethylated. And when I mean hypermethylated, what I mean is that there are methyl groups, which are chemical compounds that are bound to DNA at different spots. And in the hypermethylated subtype, they actually have more of these chemical compounds bound to more areas of the DNA. And when you look to see, are these hypermethylated subtype, is it really different from the others? So on the right here, we have something called a T-SNE plot, and it's just a fancy way to try to cluster things together and see whether groups of patients or cancers are really different from each other. And what you can see here is that there's a red cluster that differs from this green cluster right here and this blue cluster over there. And this red cluster actually is our hypermethylated subtype of prostate cancer. We don't actually quite know what it means yet in terms of all the biological processes. That's actually what we and others in the laboratory are studying at this point in time. But what we do know, if you move to the next slide, is that these patients with these hypermethylated subtypes of prostate cancer have different outcomes. And again, all these patients are patients with metastatic disease. And the x-axis represents time, and the y-axis represents, how patients are doing. And so the faster the line drops to the bottom, the worse they're doing. The less fast it drops, the better they're doing. And so the hypermethylated subtype, the patients with that actually do better. They they have longer survival times once they're diagnosed with metastatic prostate cancer that's refractory to hormone therapy than the non-methylated patients. And so what we've identified through comprehensive methylation profiling of metastatic prostate cancer is that there are different subtypes, and it turns out now that these different subtypes, these hypermethylated subtypes, have been discovered in other cancers like brain cancers and leukemias and colon cancers as well. We know that the clinical characteristics or clinical outcomes of these hypermethylated prostate cancers are different, and now we need to study them biologically. We need to understand how to target them therapeutically. And I just want to point out that all this research was sponsored by the Prostate Cancer Foundation. And so if we think about Misha's beautiful outline of a basket study, I would say in 5 years, can we have that same basket study incorporating in the epigenome and potentially the other layers of data that Misha has shown? And so I think that's my last slide, Jonathan. I'll turn things back over to you.
Thanks, Felix. Hey, Sean, go back one slide, would you, to the heat map? So Misha showed a subway map, which is a way of starting to organize thinking. The one way to think about these heat maps is you have to not go beyond medical school now to do cancer research. The second is, a second is if red is like many, if red is high, that's many subways, let's say, running down the Lexington line. And blue is not very many subways at all running down the Lexington line, just picking on randomly or but the understanding these, the activity of these genes is going to be essential in actually designing drugs, because we have lots of ideas all of a sudden about making precision medicines to just stop one subway line in particular that's making a prostate cancer and a breast cancer cell divide. But that same subway line or that same signal that creates all that red activity may be very important, but also it may be very important to understand genes that are turned off or subway lines that aren't running that make you normal again. So this is a whole epigenomics. We have some early epigenomic drugs. We're running a quiet $10 million campaign to try to launch at least 10 more of these in the same way we've had 2 FDA approvals right through COVID for DNA damage repair mutations. But this is essential. But this way of looking at a cancer patient's epigenome is going to be also how we care for every form of human cancer. And the work that Felix presented has actually given us really a framework for many other forms of cancer. Sean, you want to take it to Chris Haiman, please? So we've talked about genes in patients with advanced disease, but what if you could use all 22,000 genes to find cancers 10 years earlier or prevent heart disease? Well, how would you do that? Well, it's also a big data problem that's been reduced to research practice rather amazingly. So Chris Haiman is one of the world's leaders in population genetics, or how genes work in populations for diseases, and also is an enormous entrepreneur of scientific collaboration with over 100 collaborators around the world to get the numbers up to do this work. So Chris, could you answer the other Hamptons question is, what's a polygenic risk score? Why does it help explain the disproportionate burden of prostate cancer in African Americans, and what you think is going to happen to polygenic risk scores in revolutionizing basically how doctors take care of us?
Great. Well, yeah, thank you to the Prostate Cancer Foundation for the invitation to be part of this panel. And I think Jonathan and you and Mike have done a good job to set the stage for some of what I'm going to be talking about the completion of the human genome sequence and human genome sequencing becoming affordable. So we've really learned a tremendous amount over the past decade about the role our genes play in human disease, including for prostate cancer, and hundreds of genetic loci. So here I'm talking about germline inherited variants that have been passed on through generations, not those found in tumors. They've been found for many common diseases, including prostate cancer. And here I'm talking about these are sequences changes in our DNA sequence that exist throughout this genome associated with risk of developing disease, but they're appreciably common. They're found in many individuals. And alone, they're not predictive of risk because they only are associated with small increases in risk. However, in aggregate, a composite of all of these variants is important and can tell you something very informative about someone's overall risk of disease. And when we aggregate them together, we put them together in the form of a polygenic risk score. Can you go to the first slide, please? And this just shows an example of this sort of distribution of a polygenic risk score, where the risk is determined for an individual based on the number of variants that exist and been discovered for a specific disease or trait, their frequency in the population, whether somebody carries it or not, and the associated relative risk for each of those variants, which I indicated is relatively small. However, in aggregate, could be associated with appreciable risk. And so this just highlights this distribution of risk that may be observed in a population for a polygenic risk score for a trait, with some people having a score that places them at very high risk of disease, and others having scores that place them at much lower risk.
And Chris, this is looking at hundreds and hundreds of letters of the DNA code, right, across the genome. Right?
Exactly, yeah.
From your mom and your dad.
Hundreds of these common sequence variants that exist across the genome, right? And so this is a score that can now be calculated for any given disease or trait and used to assign people to different categories of risk based on their genetic makeup. And just one interesting thing that we have noticed when comparing these polygenic scores across different diseases, such as here heart disease, colorectal cancer, breast cancer, diabetes, and prostate cancer, is that the polygenic score for prostate cancer is really quite unique and does a much better job of identifying men at very high risk of disease, with men in this very high risk category above this blue line here having about a 5-fold greater risk of developing prostate cancer compared to men at average risk in the population. And what this is pointing to is really the importance of genetics in determining a man's future risk of developing prostate cancer.
R means relative, like R just means your risk, like that's breast cancer 2 times normal risk, right? Prostate 5, heart disease.
Exactly. Yeah. And it's all relative to something here. So these relative risks are actually being compared to the average risk in the population. There are other comparisons that can be made as well. We're comparing those at very high risk to very low risk as well. And if we do that, the relative risk is over 20. Can you go to the next slide, please? Yeah. So, something that is important to understand about polygenic risk scores. It's something interesting that we've noticed when comparing them between populations, is that they're quite different. So, for example, as shown here polygenic risk scores that we estimated for prostate cancer for men of African ancestry, which is shown in red, and those in European ancestry, which is shown in green. And you can see that the polygenic risk score is shifted to the right for men of African ancestry, which mean that men of African ancestry have a substantially higher genetic risk of developing prostate cancer compared to men of European ancestry. And it is this difference, as shown here in these genetic risk score distributions, that we believe contributes in part to some of the greater incidence of prostate cancer that's long been observed between men and African-American men and white men. And so now, I think an important question is, now we have a better risk prediction tool, that we have a stronger starting point for applying now preventative and or screening measures to those at high risk to see if we can now begin to reduce disparities in both the incidence and mortality of prostate cancer between different populations.
If this was another way of thinking about this, because we have a lot of quants, is if you just look at the go over from 1 to 2 to 4, and you were just looking at car accidents, your lifetime chance of dying in a car accident, you would be very concerned about everyone who was in the red area of the curve, because they have almost 3 times more of them are going to have a fatal car accident that you could predict at birth. You just change fatal car accident to prostate cancer. So this, and again, this is genome-wide, thanks to the work of Chris Haiman and others, looking at actually, single letter misspellings in the genome across all 3.2 billion letters of the genome. We're very, very, this is a very, very important part of the future of population science for diseases. But prostate cancer just jumps at you, thanks to Chris and his colleagues, in terms of where your great-great-great-grandparents came from, in terms of disease risk. Sorry, Chris, I get cranked up with this one.
Yeah, so it just, you brought up lifetime risk, and that's actually the plots on the bottom. So this is actually looking at one's age-specific and lifetime risk of developing prostate cancer that is now further stratified by one's polygenic risk score. So this is shown for each men of European ancestry and African ancestry. And what you see in the lines in black in this plot are the average risks in the population. So this is the 1 in 8, the 1 in 6 that gets commonly reported of a man's lifetime risk of developing prostate cancer. But you can see we can do a much better job of telling a man what their lifetime risk is based on their genetic information. The colors at the bottom in purple and in blue are those that are at the low end of the polygenic risk score distribution, where the lines to the right, the colors higher up on this plot in orange and red are those at the higher end of the polygenic risk score distribution. And so we can see that men who are in the top decile, the top 10%, have now absolute risks, lifetime risks of prostate cancer of 40 to 50%. And if you look at the top 1% of these populations, so the top 1% of the polygenic risk score distribution tail, these men have absolute risks of prostate cancer over 70. And this is just based on genetics. If we incorporate family history, we incorporate other biomarkers, I think we'll get even further stratification of men's risk of developing disease. Can you please go to the next slide? So I think the really important question regarding polygenic risk and polygenic risk scores is, how are we going to use this information clinically to improve health? This is the big challenge in the field. By 2025 or so, I do expect that the polygenic risk scores will be generated and available for a whole host of diseases, will be used by physicians and patients to guide and inform either changes in their lifestyle behaviors to prevent the disease, if those are available, or for risk stratified screening. So disease can be discovered earlier before it becomes untreatable. And I think this is conceptually very similar to what we've already been talking about how to treat cancer patients, right. Moving away from this convention, one-size-fits-all approach for more personalized approaches to treatment. And I think now it's time to think about how this personalized approach can also be applied to prevention and screening, that may be applied differentially based on one's level of risk, and may be important for some diseases or some cancers where the harm-benefit ratio of a preventive measure, the harm-benefit ratio of a screening tool is being questioned.
Right. It's really we've talked about precision medicine, precision radiotherapy, genomics, epigenomics, and now we are talking about precision screening, precision lifetime risk of disease, big data management. Anyway, the polygenic risk score is going to be, we think, incredibly important in the future of human health, and certainly in prostate cancer care. Deborah, Scher, we've got all this precision coming. Sean, you want to put up Deborah for a second? Deborah's the executive advisor to the Secretary of the Veterans Administration, and Deborah leads the Center for Strategic Partnerships and has been an extraordinary American citizen for improving the care of veterans and improving human health. But do you want to update the group that has also heard you at Bill and Mac's house, or some of you, about why the VA as a learning health system is is the nation's leader now in trying to bring all this precision care to every patient. without a marketing budget, which you do not have.
No marketing budget. Thank you, Jonathan. I think the best way to tell this story is actually to go to the next slide. And just so everybody has a picture, when we talk about the VA, what we're talking about. And I'd like to start with just a huge thank you from Secretary Robert Wilkie to Mike and Jonathan, Rebecca and Howard, and also to our incredibly generous donors, some of whom are on this Zoom call today. And I'm sorry that I can't see all of your faces, and thank you in person. But what you have created is truly an extraordinary community here. It's, you know, if you were just funding researchers, that would be fantastic. But what you have also done, if you look at this map, is you've seen, you know, in a very short period of time, this partnership was launched in 2016, you know, and it took some time to figure out exactly the path forward. By 2018, there were 2 centers of excellence. Right now, there are 12 centers of excellence. We think very quickly, with your help, there are going to be 20 centers of excellence. And why is that important? It's important because they've created an ecosystem together in partnership with Jonathan and Rebecca and Howard. We have really built a community of researchers who are bringing best-in-class precision oncology to veterans across the country and are using that platform, as Jonathan talked about and as Mike referred to, not just for prostate cancer innovation, but today for COVID innovation as well. And so many of you have heard these numbers before. There are 9 million veterans served by the VA. A third of them live in rural communities. About 22% of veterans are minorities. About 10% of veterans are women, and a tremendously growing population. And before the Prostate Cancer Foundation launched this partnership, each of these centers were doing work on their own. And it wasn't until we had the momentum and the support and the guidance from the Prostate Cancer Foundation that we could really build this nationwide network. It used to be, and some of you on this call may be associated with pharmaceutical companies. It used to be if you wanted to open a clinical trial at the VA, you had to go to every single center individually and go through every single center's IRB and then consent every single center's patients. Thanks to the incredible work of Dr. Rachel Ramoni, who leads the Office of Research and Development at the VA, and in partnership with the Prostate Cancer Foundation, who has helped us knock down some barriers and put in some very important infrastructure. We now have a central IRB. We even have a relationship with a commercial IRB. And whereas it used to take over a year to open a clinical trial, we have a great story that one of the COVID clinical trials opened in 5 days. So you're really seeing tremendous transformation of a government organization that has the scale to truly make a difference in some of the most challenging medical problems. And so, you know, the donors on this call have made an extraordinary difference in the life of veterans and in the life of the researchers who serve them. And so, you know, I thought I'd just talk a little bit about, in a short period, there are 50,000 veterans who are diagnosed with cancer every year in the VA. 12,000 of those are prostate cancer. About 3,000 have already been sequenced. And this is starting almost from zero. If you look at, for example, the Jesse Brown VA in Chicago, just recently started sequencing. 54 men have been sequenced. And so it's really bringing state-of-the-art care to the VA. But more than what you've created, you've also stimulated a conversation at the VA about what it means to lead the nation in precision oncology. So you've not only helped stand up these centers, but in many ways, the partnership has brought the VA more into the national conversation about where innovation is taking place and helped us stay current and help the rest of the medical community stay current on the insights that the VA is generating. Now, because of the power of what's been created here, Dr. Stone, who leads the healthcare part of the VA and who Mike referred to, they had just a lovely podcast together, and I would encourage all of you to listen to it when you have time. But Dr. Stone has made precision oncology one of his highest strategic priorities in terms of funding requests for the president, the budget he submitted to the president for 2021. So if you think about the evolution of philanthropy, you had Mike Milken thinking about partnering with a government agency in 2016, which many of you may have thought was a crazy idea, and now has built this incredibly powerful platform where we can enroll large numbers of veterans in clinical trials and develop insights that really transform care across America. And now we have that same government agency committing its own funding to truly scale. So it's just been a tremendously exciting time at the VA.
We're gonna hand it back to Mike because we have a lot of great questions. But Deborah, you want to talk about how it's scaled also to lung cancer and other breast cancer? But the idea was always prostate cancer was the #1 cancer, so start there. But the model would scale what Felix and Himisha and Chris have shown can be applied to every form of human cancer.
Right. So building off of these centers of excellence, the VA has announced its own internal contest to stand up 10 centers of excellence around lung cancer.
All modeled, all replica plated, to make a molecular biology joke, all replica plated off of our centers of excellence that philanthropy created.
Yes, and the VA has its first female deputy secretary this year, Pam Powers, and she has made women's oncology one of her priorities, and she keeps pointing to the Prostate Cancer Center of Excellence and says, why can't we have one of these for women's oncology as well? And there's no reason why we can't. And so there is a plan in formation to hire a director of women's oncology and to start to build out the same platform for centers of excellence around that area as well.
And then lastly, Mike, we want to get to you fielding questions. If you could join us, Mike. But one last thing, Deborah, the electronic health record has become a huge asset for COVID-19 research. It's a huge big data asset for cancer research. Do you just want to talk for a moment about why is a learning health system, the VA's electronic health record, is so advantageous in fighting COVID?
Right. So the VA was actually the first health system in the country to have an electronic medical record. They created their own and built it up over many years. And so we follow veterans from the time they leave the service to the time they leave this earth. So you can really track patients across their lifetime, track comorbidities, they stay within the system, and we pride ourselves on treating the whole person. So you have a very robust data platform to learn from and to make decisions around as we treat these challenging diseases. And so it's been a very exciting time for us, and we've just been grateful for the partnership.
Thanks. Mike, we've got questions in the chat room, but I thought you wanted to make some observations as well.
I would. One, it's good to see everyone how young they are. As we met you as young investigators, or Deborah and I spent time together 27 years ago. And I think to see the passion, so I just have a few takeaways I want to leave with everyone as we begin these questions. One, maybe 15% of all lung cancer patients who have advanced smoking-related induced lung cancer today are surviving substantially longer, and we might be using the word cured because of work done by the Prostate Cancer Foundation. And the point I'm just trying to drive home to you is that within a decade, we might not be talking about disease specific, we might be just talking about mutations. Second, work that we began in 1995 with Jim Allison, who won a Nobel Prize in medicine. 17 forms of human cancers today are now getting this checkpoint therapy. Third, triple negative breast cancer, an area that I personally began work in 1972, has a newly approved treatment that Jonathan might meant, which involves checkpoint immunology and what the potential is there. And I feel these approvals in cancer haven't made the headlines because it's hard to make the headlines today with COVID-19 pandemic affecting all of us. But the message is that cancer research has gone on. The outcome for cancer patients has improved dramatically. And the future is in using data that you saw today to analyze many of these issues. In closing, I want to, before we take the questions, Jonathan, just comment very briefly on the importance of the VA. First, largest medical record that we can access. Two, the idea that this program we launched in 14 and 15 and 16, that if you serve the country of the United States, that you will have equal access to cancer care. And as the podcast that Deborah referred to with Dr. Stone, the only place now that you have the same outcomes for African American men as you do for the general population is now in the VA. And so this program has enormous promise going forward in what we're doing. And as Deborah said, where our goal is 20 locations, we're at 12. So we continue to raise money. And I want to just comment again how uniquely positioned this is and how our promise to veterans who have served, whether they're young or whether they're old, has come to bear here, which will affect and benefit all humans. Jonathan, let me turn it over to you to ask the questions.
Thanks so much, Mike. Jonathan Evans, I think you're up first if you want to unmute. And I think this goes to Himisha Beltran.
Yeah, thank you, Jonathan. Thank you, Mike. We're starting to use the term cure for cancer, which is something that I think is relatively revolutionary. From someone's in remission, but they're cured. Is that conscious language? Is that how close are we to cure, or is it how are we doing there?
Himisha?
Okay, well, we don't use the word cure lightly. I would say that we are aiming towards cure. And in different disease states, I think we are actually achieving cure. And our goal, a lot of the treatments that we've developed have started in late stage prostate cancer, moving their way earlier and earlier. And as Jonathan and Felix talked about, oligometastatic disease or high-risk prostate cancers that were once progressing to lethal disease, we're intercepting earlier with local therapies, systemic treatments. And I think we are achieving cure in some of these individuals that we were not cured before. I think when we get to advanced disease in the exceptional responder patients, like the one that I showed, I still think it's possible. It's hard to know how often we're getting to we usually use remission or along those lines for people with very advanced disease. But with our treatments and our combinations and our more informed biologic selection, I hope that during my career or even earlier, we will be achieving cure in more patients with more advanced cancer as well. But I think overall, if you look across the spectrum of prostate cancer, we are curing more men with prostate cancer.
Excellent. Thank you.
Thanks, Jonathan. Thank your family for the Center of Excellence in Washington, the VA Centers of Excellence in Washington. There's a question, Tad Smith, if you want to come off mute. And I think this one goes both to, actually, this is a really good one, Chris and to Felix.
So, Jonathan, I actually have a question different from the one I put in chat, although I'd also be interested in the answer to the one in chat. And since you gave me the floor, I'll ask it. It's multi-part, and it's it's for Dr. Feng, I think. It's about methylation and hypermethylation. I just want to play back what I inferred from your talk and make sure I understand it. So you have the genome, occasionally or at some probability it's mutated. You then have a process of methylation, which is effectively unwrapping it. Now, the way I inferred what you were saying is that both the mutation in the genome and the expression or the methylation are necessary conditions for a bad result. Is that not correct, or how do I interpret that? And the reason that must be not correct because I didn't understand why hypermethylation was correlated with better results. So that was my question. I didn't want to put in chat; it was too complicated. Thank you.
So great question. What I would say is the answer is that it's complicated, and that doesn't surprise you. So number one, yes, mutations are associated with, certain mutations are associated with worse disease and so forth. And in order for that gene to be accessible, it, for the most part, needs to not be methylated. But I also want to point out that methylation is a fluid state. So things that are methylated can become unmethylated and vice versa, whereas mutations are more, if you've got the mutation, you've got the mutation for the most part. It's not going away. And so in general, in order for a gene to be accessed, it needs to be unmethylated or focally less methylated. The reason why hypermethylation may be associated with better outcomes is that there are certain genes we want turned off in cancer as well, right? That also gives us therapeutic strategies as well, if we can understand that part better.
I think for some of our listeners, let's talk about what methylation is.
Yeah.
Etc.
Yeah. Felix, help me with this, but it is complicated, but if you think of it like a dial, right? And the more, if it was an old stereo from 1978, just the more you turn clockwise, the greater the volume. So methylation is a way of turning the dial down, and hypomethylation, or taking the proteins off the DNA tape, is a way of turning the dial up. And then the question is, what's being turned up or down? There's certain genes that are like brakes, and there's certain genes that act like an accelerator. So you have to know, and this is how nature works. And this is why you don't have toes that are 20 feet long, because the genes involved in making your toes will have a dial that go from hot turned way up, right, which is to turned way down, so your toes. So the cancer corrupts. In order for a cancer cell to grow and spread, it starts to corrupt all the dials and all the genes. And Felix is right that the more unwound the gene is, the more the DNA tape can be seen to be played, the more the volume is up, or more signal is up. And this Hamptons group is seeing, really for the first time, our attempt at public education in this area. We want to work on how to explain it, because every cancer patient needs to understand it. But until Felix published his paper, you're only about 60 days. This group is only 60 days behind the whole scientific community of understanding it. But it's just like, I don't really understand how my iPhone works. For a clinician, I need to understand how the app works. And there will be a epigenomic app, as Himisha showed, as Felix has talked about, for how to care for every cancer patient, something like that.
And just to add to that, Jonathan, very briefly, Tad, I think the ultimate goal here is we want to turn up the dial on certain genes, and we want to turn down the dial on certain genes. And so really it's the therapeutic potential that we're excited about.
Right. Chad, you want to ask your Moore's Law question? It's a
Oh, sure. So these are for Dr. Beltran, I think, or at least it was her position. It was her presentation that prompted them. So classic, does this sort of Moore's Law notion of every 18 months a doubling in productivity apply to big data and genomics and what we're learning there? And then the sort of subsidiary question or related question was, I had always understood precision assays and precision medicine had been limited because it's expensive and costly to produce a cure or an assay for a otherwise small or very specific mutation or a low probability group of patients in the population. So the question I was raising there was, is technology and the plunge in technology cost making it highly scalable, more flexible, and much, much more economically sensible to do precision medicine at scale, even though it might affect small populations? And I was particularly intrigued by the notion, I think it was you, Jonathan, that jumped in and said, well, what you could do is you could be aggregating 3% of this particular cancer, 4% of that, 7% of that. But that's a partial mitigant. But at any rate, so that's the question.
Well, you're talking to the right person.
I think, you can correct me if I'm wrong, but I think that the cost of genomic sequencing roughly followed Moore's Law initially and then exceeded that, really dropped precipitously. And so the first genome was 10 years, $1 billion, and now it's like $500. And there's different, when we talk about DNA sequencing, there's different types of DNA sequencing. And the ones that are now really scalable, we're seeing at the VA, every center is capable now of doing the DNA sequence. And so now the challenge is really application of those results towards improving patient care. And one of the challenges has been, as you scale this, how do we know about that 2% of patients, what happens to them? And that's where integration with the medical record is really important. Designing the basket studies to be able to act on them. And then, thinking about the cost of sequencing coming down, and now insurance is actually paying for some of this. Where are we going? So now the cost of epigenetic assays are also extremely expensive, or some of the other ones, but we also predict they will drop at the same rate. And as we generate all this, we need to sort of invest in that. I think that's where, at least in many cancers, we had to invest a lot up front for the long-term gain. And I think that's where we're hoping some of the other assays fall. So I do think that the scalability has been achieved with some of the assays that we're talking about. When you want to go beyond, specific genes and do the whole genome, we get a little bit more complicated, and it becomes into data storage, interpretation, and again, the application of the results. But I think other people can chime in if they have, Jonathan, if you have anything else to add to that.
No, but PCF is a data science seeking foundation now, and the electronic health record, as Mike has said so eloquently, the electronic health record has to be totally rethought because that's the obvious implication. I don't know how fast the electronic health record really is revolutionized, but that's a major barrier for patients right now. The good news is Deborah was very polite about this, but after Memorial Sloan Kettering, really veterans right now, more than 3,000 veterans have just gotten a precision decision making done with our program in community hospital settings with cancer center faculty and new dedicated data managers and research nurses, or Mike says the new data manager, the new data nurse of the future, the big data nurse of the future. But we basically need a whole new way of thinking about cancer care and big data and empowering patients to know that they need it. Chris Evanson asked a question for you, Chris Haiman, which is in the chat, is how can this amazing story about polygenic risk be communicated to community urologists and family practitioners?
Yeah, so it's a little bit early to say. Some polygenic risk score companies are actually already advertising this test. Some urologists are currently using it. For example, Ambry Genetics, they include a polygenic risk score test alongside their gene panel mutation testing. Unfortunately, now it's being provided to a cancer patient, so your risk of cancer, if you've already had the disease, is unfortunately not very informative. But I think really what's going to be needed is a randomized trial. I mean, we do need to go back to the chalkboard and conduct a randomized trial where we integrate this genetic information with PSA to better understand the harm and benefit of PSA plus this risk score. Is it really going to improve the detection of lethal tumors, at the same time reduce the overdiagnosis of indolent disease? And that's the expectation. But hopefully we will in the near future, through I think collaborations with PCF and NIH, be in position to conduct that trial. So this information, hopefully when successful, will be then polygenic risk score will be available and communicated to urologists with a clear understanding of how it's used. At what point do you act on somebody's genetic risk? At what age? And I think we need to get other public health researchers involved, including genetic counselors, to be able to communicate with urologists and guide them in terms of how they should be talking to the men that they treat.
Thank you.
Jonathan,
Mike,
I know we only have a couple minutes left, and I thought I would like to make a couple of summary comments. One, we began this podcast series to let each of you know what individuals with significant responsibility and leadership were doing at a particular point in time, so that you could see their decisions and you could see the dramatic changes that have occurred. The early April interview with Alex Gorski, CEO of J&J, which is the most valuable healthcare company in the world, they were talking about what they're going to do with their vaccine, make it available at no profit, and put it into humans in phase 1 in January of 2021. This was in April. Well, in July, 3 months later, not 9 months later, it went into phase 1. So they accelerated dramatically the use of their technology and their vaccine. In this next month, coming up next week, they expect to have 300,000 people enrolled in phase 3. And so as you go through, and we had put up a slide earlier, but as you go through these podcasts, 1/3 of them have individuals that are involved or have touched cancer or other medical areas that are available to you. And there is a slide, maybe it will come up or not, just showing you the names of some of these that you can access. And we spoke about Dr. Stone at the VA and so many others. The second thing was the diversity. So half of the people in the first 50 work for nonprofits, half of them work for for-profits. From that standpoint, the slide that you're looking at gave you the diversity of the areas they worked in, but it showed you the numbers here where there were 11 companies, CEOs, or private, that employed more than 100,000 people. There were 17 that employed 10 to 100,000. There were likewise 11 that employed 1 to 10,000 and 17. And so we try to get a diversity of viewpoints, and the group in just the first 50 employed more than 2 million. And you can see here just the large number. 21 had MDs and 14 were PhDs in this diversity. The tracker we spoke about today, more than 203 vaccines. 20 to 30 are in humans, but we are tracking more than 203 vaccines that you can go on and see. And likewise, between antivirals, antibody, immunology agents, more than 316 of them today. One of the areas that's become very important was BARDA. The the Biomedical Advanced Research and Development Authority. And as we reached out to BARDA very early, Dr. Simons, myself, and others, it was created and established to aid in securing the United States from chemical, biological, and other threats, as well as pandemic influenza and emerging infectious diseases. And it is this organization that we've spent a lot of time with who has agreed to fund, build manufacturing, and given the go-ahead by funding the doses of various vaccines, antivirals, antibodies, before we know whether they work or not. And we will talk about what is on tap tomorrow morning at 10 o'clock Eastern, 7 o'clock on the West Coast on really COVID-19. And as we pointed out, more than 70 of those 500 therapies have found their way out of the cancer research movement. One other thing I want to mention to you is we came out with a new periodic table, and it came out of PCF, and it was focused not in when you and I were all in school and we studied what nitrogen was or helium or boron, etc. But it was an outgrowth of the work of almost 3 decades of the Prostate Cancer Foundation and sister organization Faster Cures on if you could change your microbiome, could you change how your genes were expressed, and can you change your own outcome? And so these involve fruits and vegetables and other things that by you changing your diet. So on Sunday morning, Beth Ginsburg, who has been taking the data that we've had now for 25 years and creating new recipes, will be showing you how to make food that tastes great and also can help change your microbiome for your health. So yes, maybe chocolate pudding is on your diet, but with silken tofu, not with normal ingredients. Yes, you'd like to have fruit tarts, but substantially less sugar, etc., and how to make those. Lentil bolognese to get the protein in your body if you're a vegetarian, but also chicken or turkey or other forms of bolognese. And lastly, for everyone, how to make chicken with a lot of vegetables. So hopefully it'll be fun, and we'll see you Sunday at noon Eastern, 9 o'clock Western. Jonathan, I want to thank you and the team that joined us today. We've recorded this. It will be going up on the PCF website. So if you have any questions, but I think the question that Tad Smith said is so interesting because we have genes that control and potentially impede the growth of cancer, and we have genes that accelerate through mutations the growth of cancer. And so the simple idea that you just want to knock certain things out, some things we want to enhance what they're doing, and some things we do want to knock them out. And also, today you got a preview of why we've been able to bring control by working in a partnership with the VA, a substantial reduction in the death rate for people that served our country, and also the promise of big data on how we're going to essentially, ultimately someday, use that word cure in cancer. So thank you for joining us. We look forward to seeing you on Saturday at 10 o'clock Eastern for the discussion of COVID-19, and Sunday at noon for Cooking with Beth.